All right, well, I will begin with a word of prayer. Dear Father, we thank you again for this opportunity we have to meet and study your creation. Just pray that you would be glorified we do, that we'd just have a good day to prepare for test one, Lord. In your name I pray, Lord Jesus. Amen. You guys excited about the test? Yay? All right. Very good. So, let's see here. Let me go over, and we'll start with, let's go back to the beginning, right? Do you have your surprise attack mission 5 you want to give me? Yeah. So to start, what did we do to start with? We just had, what was the first question I asked you guys? If the differential equation below is exact, solve it, and what? Thank you. If not, explain why not, right? So this one here, of course, now that we know about differential forms, we could take a different approach, right? You could just take the exterior derivative of these equations, and if the exterior derivative is non-zero, then it can't be the case that you're looking at like df for some function f, right? But anyway, the first one, if you just kind of integrate this, you get one, where was I? For part B. So for part A, that's not exact because if we take the y derivative of this, we get 1, right? But if we take the x derivative of that, we get 0. So the closed condition fails, therefore it's not exact, right? Of course, the other thing you could do would be to try to do partial integration of the coefficients of x and dx and dy, and you get a contradiction if you tried that, you know. But the other one, what I usually do for part B is I just integrate and I just guess it pretty much is what I did here, I think. I just said, okay, well, if I put x squared y squared and then 1/2 sine x squared and minus 1/3 e to the 3y, then the total differential of that is that, which is what I have. Consequently, that f equal to a constant is the solution of df equal to 0. Simple as that. Now, of course, that begs the question, how did I guess that, right? But I think for something as simple as this, it's not beyond the realm of possibility that you could also make such a guess because you guys have had calculus 3 and you understand partial differentiation, so it's not like such a big jump that you could do this kind of integration in your head, right? But there is another way, which is so I simply guessed f and checked that df is in fact m dx plus n dy for the given m and n. But, oh man, wait a minute. Oh, page 1, I'm an idiot. I was on page 2 of my solution. I'm like, I'm missing something here. Oh yeah, duh. So back on page 1, I solved A, which is just what I said for you guys, right? The partial m, partial y is 1, but partial n as in nenu, partial x is 0. Of course, 1 is not equal to 0, not exact. This one, on the other hand, we're trying to solve partial f, partial x is equal to the coefficient of dx, and partial f, partial y is equal to the coefficient of dy, right? And in order to achieve that aim, I have to solve these two partial differential equations, right? So the way to do that more rigorously is to integrate the first one with respect to x. If I integrate that one with respect to x holding y fixed, that gives me equation 3, which is that f of x comma y is, x squared y squared plus 1/2 sine of x squared plus some constant in y, right? Possibly some function in y, right? And then I take 3 and I plug it into 2, and when I do that, that tells me that, in fact, the derivative of my constant in y, my derivative of my function in y here, with respect to y, must be equal to e to the minus e to the 3y, which then I can integrate both sides and get minus 1/3 e to the 3y. So like the distinction between this solution and the first solution I looked at is that we're integrating one at a time, adding a constant of the variables that we're holding, adding a function of the variables we're holding fixed, right? Because it's kind of a partial integration. And if you do this method, right, this solve one, substitute into the other method, and it's actually not possible to find the f, you will get a contradiction in the substitution. Like the fact that the closed condition is met here is borne out in the fact that you get the same term here and there and they cancel, and it just leaves you with, just a function of y being the derivative of c1. If it's not exact, when you go through this process, you end up with like the function of y is equal to something in terms of x and y. Here, that's what would happen to you if you did such a thing. This should all be vaguely familiar because it's really the same calculation as we did in Calculus 3 to find the potential energy for a conservative vector field, or to find the potential for a conservative vector field. It's the same calculus, but just in 2 dimensions, right? So there's that. Then find the explicit solution of e to the x dy dx equal to 2x. Well, we separated and then we integrate by parts, right? Need to know integration by parts. I said in the announcement, but I'll repeat again here now. You are allowed a scientific non-graphing calculator for the test. You cannot bring a TI-89, TI-92. Any of these like calculators that involve symbolic differentiation, integration are not allowed in here on the test. So just to be clear, and you shouldn't need them anyway, but well, I guess you might need it for the integration here, but that's kind of the point. You should be able to integrate. So anyway, we separate, we integrate, and there's a solution. Explicit means we solve for y, which is kind of a non-event for this problem, right? Solving for y is kind of, yeah, well, there it is. Solving for y in other problems has been more involved, right? Like this one, it's slightly more involved. This is a linear differential equation after we divide by x, right? So since it's a linear differential equation, we use the integrating factor technique, multiply by the exponential of the integral of the coefficient function to y, which in this case is 4 over x. That gives us 4 natural log of x, but we can simplify that to the absolute value of x to the 4th, which is just x to the 4th. If you do get like absolute value in your integrating factor, just drop the absolute value because you're just multiplying the whole differential equation by that. You don't need absolute value there, right? Absolute value is plus or minus the thing. Since you're multiplying the differential equation, just drop the absolute value when you multiply if you did end up with one. You don't need to keep it. Anyway, because the calculation you're doing, it's either going to make sense for the absolute value positive or negative, but not both at the same time anyway, so you don't really lose anything doing what I just said. But anyway, so multiplying by x to the 4th, we get this, which then reverse product rule gives us that. Integrate both sides. We get x to the 4th y equals to all this. It's important that when we do the integration, we add the constant. See, because by doing that, when we solve for y to find the explicit solution, we end up dividing that constant by x to the 4th. You can't just do the solution and then at the very end add a constant. You'd be wrong, right? So we have to like do the calculus. But you guys can jump in at any point if you got a question. I just thought I'd run back through the surprise definitions. That seemed like a good path to take today. So I'll keep doing that. Surprise attack mission 2 was more exciting. These are more applied problems. And the applied problems that beset you, I've asked you to find an orthogonal trajectory of this given differential equation. I asked you to find an explicit solution to this by a substitution. So this is not really an applied problem so much as this just is a substitution problem, right? But we hadn't got to the substitution by the time I did surprise attack mission 1, right? So I put it on 2. The other kind of application, so we did orthogonal trajectories. We also did find the integral curve of a vector field, right? So you should be ready for those questions on the test, right? If I ask you to find orthogonal trajectories, you should know how to do that. If I ask you to find integral curve of a given vector field, you should know how to do that. If I ask you to solve a retarded spring problem, that's what they're called. That's what they're called, right? It's a spring with friction. It's a retarding force. So the retarded spring problem you should be ready for, and I think that this problem 4 was the Kool-Aid problem, right? That's a mixing tank problem. We worked an example like that in class. You should be ready for one of those. Problem 5 is a direction field problem. Those are actually pretty easy. You just have to understand the relation between the geometry of the direction field and what a differential equation says about the slope of your solutions, right? So that's not actually bad. And like, I don't have the direction field in front of me to look at, but like, if you think about the analysis, when you look at the picture, the D1 this differential equation, right? That is slope, everything's slope 1/2. So that's like obviously lines with slope 1/2, right? And if you look at D in the given pictures, it's pretty obviously that one. 2, this is undefined when that's negative, right? So that's kind of a dead giveaway. Given the 4 pictures, there's only one that's ruled out like a half plane below -1, right? So like this has to be that one. And then these are a little bit more subtle, but essentially we should have horizontal tangent lines at such points as x is plus or minus 1 and y equal to 0. And if you look at the given direction field, you can see that that's the case for number 4. But anyway, let me get back to the problems here. So to find the orthogonal trajectory, what do? Take the dy dx that you're given, right? Now sometimes you have to find that from a curve, right? Like I don't have to give you dy dx given. I could give you, an equation that involves x and y. You might have to implicitly differentiate that to find the dy dx given using calculus 1, right? That could happen. But once you do that, once you find dy dx given, you do -1 over that and solve for that. That's going to give you trajectories which have negative reciprocal the slope of the ones you're given, and those are so-called orthogonal trajectories. So here, that just gives me this problem, which I separate, integrate, and the usual. Now here, you got to be careful because I had y is negative, so we must in fact choose the negative solution to match the negative, which then ends up giving me 2c is equal to 1, which finally gives me this here solution down here. So, substitution problem, it's, these are not hard. You just have to do the math. Pretty much, because I told you guys that I would give you the substitution, so that's the hard part. Like if I didn't say, you have to create this substitution, that would be much harder, but I didn't do that to you, right? Because I'm an easy professor, spread the word. And I'll prove it to you Wednesday. You'll see. Legends of my easiness will spread from this week forward. I will no longer be known as the hard professor. I will henceforth be known as Dr. Cook, the easiest professor in the math department. It will be known. You didn't see in person?
Oh, no.
Okay. I'm talking to that person there, I guess. I don't know. Use your imagination. Maybe like a little person, maybe? I don't know. Apparently. Whoever it is, I'm looking down at them, but well, that doesn't help. Dang it. Anyway, so we just, I don't know about you, but I don't like differentiating quotients. So I take a quotient when a product will do, and then differentiate it, right? It's just a good move to solve for y in the substitution, because then you can substitute dy dx for this stuff, right? You have to somehow or another replace the dy dx with your substituted variable dx, right? And then replace these with the substituted variable. And of course, once you do that, oh, this problem is so lovely because it's just dv over v squared plus 1 equal to dx over x. You integrate, inverse tangent. Everybody knows integral of 1 over 1 plus thing squared is the inverse tangent, right? We all know that. We should certainly know it now that it's been covered in the surprise attack mission. And on this other side, you get log. And then, of course, we have to unsubstitute, which brings us finally to y equals to x times the tangent of c plus the log of the s value of x. Hooray, solved, right? So that one's actually not too bad. Now, the integral curve, remember, as I've explained to you guys, we're trying to solve dy dx is equal to q over p. That's going to give us the integral curve, all right? I mean, you could think about it more basically as like dy dt divided by dx dt, where dy dt is this thing and dx dt is that thing, but then the t's, they be canceling, so it just gives us back this Cartesian problem. That's what I'm talking about here, eliminating t for now. So you've got dy dx is equal to this over that, which is this over that, which then, of course, we know partial fractions because we've had calculus 2, yay. So, I mean, putting calculus 2 on your test makes it easier because that's prerequisite material. I'm not even teaching you on the current course, I'm testing you on the previous course. In that way, I am an easier professor than the professors who don't test you on the previous course and just test you on this course, if you think about it, right? No? That doesn't work that way. But you should know partial fractions, right? If I was to ask a question like this again, you shouldn't be like confounded by it. You probably can do it. Now, so finding our way to the implicit general solution is easy enough, right? And if I wanted to go from there to explicit general solution, what would you do? I'll write it out here. I would do y plus 2 equal to minus 1 over natural log x minus 2 minus natural log absolute value of x minus 1 plus a constant. And then, lo and behold, y is equal to minus 2 minus 1 over natural log. I mean, we could simplify, but I'm intentionally not simplifying at the moment just to communicate a point. This right here would be the explicit general solution, right? Now, that's not what I did, is it? What did I do? I solved for C. Why did I solve for C? What was the deal? This problem was a little bit different, wasn't it? I didn't just say find the explicit general solution. What did I do? Oh, man. Yeah, I think I had an initial data point, didn't I?
Yeah, it was, you wanted the integral curve through the point x naught, y naught.
That's right. So I had that pesky point x naught, y naught that we wanted to find the integral curve through. So see what I did was I plugged in that point to solve. I mean, I solved for C, right? And I said, well, C has to be whatever it takes to get minus 1 over y naught plus 2 plus the natural log of x naught minus 2, this, right? And then what I did past that point is what is known as algebra. And so if you look at what I did, I just put in that constant here. And then if you notice this step right here, what am I doing? Log of a sum is the log of the product, right? So see, I took this addition of logs to a log of a multiple. And then I also put this out front, and then finally I reciprocated both sides, and that's it. That's all that happened there, okay? And you can check that the answer makes sense, right? What happens when you put in x equal to x naught? Do you see what happens there? You get x naught minus 2, x naught minus 2, x naught minus 1, x naught minus 1. In other words, you get the natural log of 1, which is natural log of 1 is 0, right? So this just simplifies to y naught plus 2 over 1 minus 0. So y naught plus 2 minus 2 is y naught. So you plug in x naught, you get y naught. My solution checks, right? So sometimes I ask you guys to find a curve that goes through a given but arbitrary point. And this is the kind of mathematics you have to do. Algebra, all right? So this one is just a mixing tank problem. It's a lot of words, but there's really not much here. Basically, the point is you set dy dt equal to rate in minus rate out. And so y divided by 1,000 gives you the concentration of Kool-Aid when there's y pounds in the 1,000 gallons. And 25 gallons per day is how much we're pouring out. So then I just solve for dy. I separate, integrate, and then I use the story of the problem. It says I'm looking for when there's just basically 5 pounds of Kool-Aid left. So that gives me the equation 5 is equal to 20 e to the minus t over 40, which anyway suggests about 56 days. So anyway, we move on here. So let's see here. So the test is probably something like 40% the first order material, 60% the later stuff. So it's probably more about this than it is about what we were just talking about. So you need to make sure that you can do these kinds of problems efficiently and correctly, right? and double check your work, because it's so easy to solve a quadratic equation wrong and convince me that you don't know what you're doing, when maybe you do know what you're doing, you just solved the quadratic equation wrong, right? But the details matter, all right? This is the kind of speech I give right before we find a mistake in my solution. So I fixed it here, though. I had one here, but I fixed it. So this, of course, you could just factor like a normal person into like x, d plus 1 times d minus 5, right? But I completed the square because it's just how I am. And anyways, that gives you 2 plus or minus 3, which gives me these characteristic values, and hence c1 e to the minus x plus c2 e to the 5x. Any questions about this? Yep.
I have my c1 on e to the 5x and c2 on e to the 5x.
Oh, you could go either way. Like the labeling of the constants is not, that doesn't have any specific meaning. We can always switch the order of the constants. I don't, if you're finding some particular order in my answers, it's completely coincidental. I mean, if you wanted to pick an order, I guess you could always go like smallest to biggest or something, but then you got the complex ones to worry about, so we got to give an ordering to the complex numbers. Well, that's a trouble. I guess you could give it the lexicographic ordering if you wanted, but who wants to do that? Problem 2, we had plus or minus 3, so there's 2 ways to go here. The one is like e to the 3t, e to the minus 3t. Why t? Well, because I told you dy dt is y prime, right? That's why the answer here is in terms of t, whereas up here it was in terms of x. But there's another way of formulating this, which is cosh and sinh. So you got these 2 choices. Sometimes I like the cosh and sinh of 3t. This one here is repeated root, so I have to multiply by x, because we got x for the independent variable. The next one is unpleasant, but certainly something we could do, and we should be ready for. Could be unpleasant. And I would expect an exact answer, not like a decimal answer on this kind of thing. So I would be looking for exact radicals in this particular kind of problem, but not in my physics course. But anyway, so I complete the square. I end up with minus 3 plus or minus the square root of 29 all divided by 2, which gives you these 2 characteristic values. This one here, we can factor out a d squared, and then we get d plus 6, d minus 6, d plus 6, which gives me c1 plus c2t from the d squared, and then e to the 6t, e to the minus 6t over there like that. For problem 6, I said find a constant coefficient ODE of smallest degree, which has solutions t plus cos t and e to the minus 3t sine 7t. All right, so I look at this, I go, oh, okay, I can get that. Well, the t I need a d squared for, right? The cosine t, well, that comes from d squared plus 1, right? So this and that picks up that. But I also need to get this guy. That's coming from lambda equals to like minus 3 plus or minus 7i, which through that theorem we worked out in class, I can write down the d plus 3 squared plus 49 factor to pick up this as a solution. So I multiply those 2, and then I get all of that jazz. So the lowest order ODE, which has this and that as solutions, is actually 6th order. That's a pretty mature version of this question. There are easier versions of this question to ask you guys, but if you really, really understand problem 6, you've understood a good amount. How about this one? Problem 7. Find the minimal annihilator for the function t squared e to the minus t. All right, so this is coming from lambda equal to minus 1, 3-peated, right, to use a technical term. And so my annihilator, just d plus 1 cubed. That'll do it. That's all I need. All we're doing is reading the solution theorem backwards, right? Yeah.
I factored mine up, and you took away like 1.5 points out of 2.
Oh, well,
Did I do too much for it, or?
no, it's just that the grader didn't understand what you did. I'll give you your points back.
I did that on problem 6 and 7.
Yeah, I usually try to leave like instructions like do not multiply out, but I didn't do that there. So it's not wrong. What you did is actually better. It's good. So I wouldn't want to penalize you for that, obviously. So I'll have to go punish the grader severely. Who graded this? 2 people. Oh. I knew who it was. Wait a minute, was that person? Huh. I don't remember. Anyway, I mean, there's 2 choices. I only have 2 people grading for me. I just got to figure out which one it was. I'll figure it out. I'll have my pound of flesh. Let's see here. So the minimal annihilator for this one, here we've got -1 plus or minus 3i. That t tells me it had to be repeated to get that. So that's like a, d plus 1 squared plus 9, square all that. So I've got this quartic operator. And again, if you multiplied it out, that's okay, but I actually don't care about the multiplying out so much. In this context, there's another place where multiplying it out is essential, but this is not that place. So here you're supposed to set up the correct form for the particular solution. And so here it turns out that the homogeneous solution's got a cosine and a sine in it. So that's got overlap, but this doesn't. So for the x e to the x, I would just do a e to the x plus bx e to the x. That's kind of like the naive form of the particular solution for this due to that piece right there. But then the cosine piece being overlapping, I end up having to multiply by x. Again, the annihilator method derives that for us. Here, this has homogeneous solutions like a constant and also e to the x, so that e to the x is overlapping, but the x squared and the sine is not. So I have like, well, anyway, let's just look at the solution. Let me not try to talk through that. There's a lot to talk through there. And problem 11 is just straight up an operator calculus problem. So problem number 9, I worked through the annihilator method. I'm like, okay, y prime prime plus y equal to that. So my annihilator for this is d minus 1 squared times d squared plus 1. D squared plus 1 kills the cosine. D minus 1 squared kills the x e to the x, all right? So that's my minimal annihilator. And so this, my differential equation was d squared plus d squared plus 1 acting on y equals to g. So I annihilate the differential equation like so, which turns this non-homogeneous differential equation into this homogeneous differential equation, right? And so I look at it and I go, oh, okay, well this right here is the homogeneous part, right? Or if you like, the homo part. And so the rest is the particular solution, or you could call it the no homo part. So the no y sub no homo is all this right here. And what? Something? This is my son's idea. It's not my fault. Your generation is so much more based. Anyway, we've all been taught to be polite. But yeah, so that's the form of the particular solution. To find the details, A, B, C, D, we'd actually have to take this and plug it back in here, double differentiate it, add it to itself, and set it equal to that to find the values for A, B, C, and D. But this question wasn't that. It didn't say solve. It just said set up the particular solution. So I did that. Now the next one says solve. So we're going to have to face the music. Now I think I was lazy. I didn't show you the annihilator method for problem 10. I just wrote down, okay, so if this is the homogeneous solution, C1 plus C2 e to the x, then the naive solution for x squared is ax squared plus bx plus c. But because there's this overlap, I have to multiply that by x, all right? And likewise, the naive solution for e to the x would be just d e to the x, but because there's an overlap, I multiply by x. On the flip side, the sine of 2x does not overlap with a homogeneous solution, so the naive solution for sine 2x just is what it is, all right? And there you go, that's my particular solution, just the setup. Now I work it out. So I differentiate, I double differentiate, I reorganize my stuff, and I equate coefficients down here, like so, and out pops some equations like d equals to 1, and b equals to 0, c equals to apparently minus 2, a is minus a third, and the e and the f, they kind of play their own game over here, and they work out to minus a fifth and a tenth. Put it all together, we got, this is our solution. So that's that's a pretty good problem. I think that's just about as hard as they get. If you can work this problem confidently and really understand all the parts, including how you set up the YP, I think you have a pretty decent understanding of these kinds of problems. Of course, we can go one step further, right? I could give you initial values. I could give you like initial position and initial velocity, and you could find C1 and C2 from that. So there is yet more you could do here. And this one, we just have to work it out, right? Like TS acting on Y gives me this, which then if I factor the Y out, I've got like a 3x squared ddx plus x squared d squared dx squared acting on Y. On the flip side, when I do ST acting on Y, I get, so the important thing here, guys, and you might not appreciate it until you don't remember to do it, which is you have to act on a test function to see the pattern. If you're not acting on a test function, you will not be able to see your way through all of the product rules and everything in your head. It's important to work on a test function to see what the pattern is. Like in this case, ST, this is T, and then S is 3 plus the derivative of whatever T did, which ends up giving me these terms, right? Now the thrice x squared dy dx is simple enough, but over here, ddx, well, it's hitting a product, so I have to do the product rule, 2x times dy dx plus, x squared times d squared y dx squared, and then I just put everything, like factor the y back out and think of it as a differential operator. And so this is the formula for ST, this is the formula for TS, and then of course when you take the difference of these two guys to calculate the commutator, a lot of stuff cancels, like the 3x squareds cancel, and the x squareds, ddx squareds, they be canceling, but we're left with the minus 2x ddx, so that's why that commutator is that. This is not hard, like everyone can do this problem. If you're not seeing it yet, take a half hour of time and like meditate on it until you see what's going on. It's not that hard. Everybody can do this one. The scan of this is kind of sketchy. Sorry about that. It's just, I don't know, we've run out of white paper in the math department somehow, and like there was just gray in the printer when I printed this, so I'm like, but whatever. This one's a little sneaky because, well, I guess it's not too sneaky. Basically, there's overlap on the sign, but not the cosh, right? So when I form the particular solution, I have to multiply the sine piece by t, but not the cosh piece. Cosh, for me, the natural way to look at that is a cosh plus b sinh. You could alternatively have converted this to 1/2 e to the t plus e to the minus t, and then done like an a e to the minus t plus b e to the t term for your like cosh. Like you could split it up, and you can take the coshes and turn them into exponentials and work the problem like that if you want. That's also fine. You'll get the same answer I do. But anyway, again, we differentiate, product rule, keep careful with grouping stuff, and after a bit of algebra, we will find that we can equate coefficients of the linearly independent functions cosh, sinh, cosine, sine, and get these four lovely equations, which gives me this general solution. Here's the homo part, and here's the no homo part right there. All right, so, or I'm sorry, homogeneous and particular. But the homo part is very degenerate, by the way, because you've always got C1 and C2, so there's like infinitely many solutions in here. So it's very, very degenerate. But anyway. Any questions? No? All right. Yeah. So this is a retarded spring problem, but this time with an external force, right? And this was bad. This was a very bad typo. Like, I definitely wanted b squared minus 4mk less than 0. And the reason for that, if I do that, then this definitely does not overlap, which means I don't have to do the multiply by t thing for the particular solution, which I definitely don't want to do for your problem here. But anyway, this is just like the problem we just worked. It's just symbolic. All right? So. This one here, I hope you guys understood. This is like, you do need to know variation of parameters. So this is the basic question, is when do we use variation of parameters? Do you guys know? when to use variation parameters, when to use undetermined coefficients, like which one do you use and why?
You want to use variation of parameters when your differential equation is equal to something that's not the easiest to like simplify or annihilate. So like on this one, it's e to the negative x over x plus 1, and that's not a very pretty thing to annihilate or easy at all, so it's easier just to do the variation of parameters.
Yeah, let me put it, you're exactly right. The thing is if whatever appears here is the non-homogeneous term, the inhomogeneous term, the forcing term as it's called, because it corresponds to like an external force on a retarded spring or a voltage source on our LC circuit. If that, whatever that is, that inhomogeneous term is not a product, a sum, or a difference of just homogeneous solutions, you cannot do undetermined coefficients. So this is a quotient of homogeneous solutions, but that doesn't matter because quotient, we don't get those. If you look at how the solutions work, we get like products of polynomials times exponentials times sines, but that's it. We don't get tangent, we don't get secant, we don't get natural log, any of those things. Those are not part of the homogeneous constant coefficient problem, right? So anyway, so this is definitely a variation parameters problem because it doesn't fit the other method. And more to the point, variation parameters is a weapon of last resort, right? We'd prefer to do undetermined coefficients if we can. One exception to that, I would say, if your inhomogeneous term is arbitrary, if you just know it's like g, it's just some arbitrary function g, well, variation parameters is the thing you want to do for that. Because if it's just an arbitrary function g, the best you can do is like find an integral solution, and variation parameters finds the integral solution for you in short order. But variation parameters says we take the inhomogeneous term times the second solution in our fundamental solution set, and we divide by the Wronskian of the fundamental solution set. And however that works out, that's the first parameter. The variation parameters v1 and v2 are the parameters in the system. There's v2, and then you put it together. And the way you put it together is, well, I guess I just decided to add in the homogeneous solution this time, but it's the y1 times v1 plus y2 times v2. And sometimes what happens when you do that, sometimes some stuff simplifies down, but whatever, I mean, that's it anyway. So we also talked about the Cauchy-Euler problem. Remember, the Cauchy-Euler problem is really different in the sense that instead of guessing y equals e to the lambda t or something, or e to the lambda x if you like, we guess y equals x to the r. And when we plug that in, we get like an r times an r minus 1, an r for this, a 9 for that, which gives us r squared plus 9, which is giving me plus or minus 3i for my r. And then, like the story is, we take the real part of this, the imaginary part of that, but remember that x to the 3i is cosine 3 log x plus I sine 3 log x. So that's the real part, that's the imaginary part. We are always interested in real solutions here. There should not be an I in the finished product. All right. And this is a variation of parameters problem. And there you go. That's the general solution, just like that. What's that?
It's very beefy.
Yes, it is. It is beefy. But in some sense, this is easier than the last problem because you didn't actually have to do the integrals. You just had to set them up. Right? So. And this one here, I tried to give you guys like a very heavy-handed example in class the other day that kind of set you up for this. I think this one actually is easier than what we did in class. Like a lot easier. But here's what I was talking about in terms of multiplying out. Here's where multiplying out matters. You know, multiplying this operator out is what we need to do in order to divide it into the other, in order to find the cofactor of, in fact, d to the fourth minus 81, which of course factors nicely into d plus 3d minus 3 times d squared plus 9. And once you have that, you can solve the thing, right? Yeah. And then last, well, probably least important for your test, but I mean, I'll put like a token differential form thing, but it's not going to be more than, like 5-10% of the test probably. But here's that. Would you guys have any questions about this? I mean, so like A had d omega was 0, and that is because you end up with that. Take the exterior derivative of this and that. I mean, the exterior derivative amounts to taking the differential of this and that, wedging it with dx and dy, which ends up giving me this. But omega is nothing more than the differential of x cubed y minus x squared plus tangent y. So therefore, this equal to a constant is the solution of omega equal to 0. Do you notice what I didn't even write? Like we have this habit of writing f equals to stuff and then putting f equals to a constant for the solution. I haven't even written f here. I just have seen the solution directly from the level of like differential calculus. And what I mean by differential calculus is like calculus of differentials. So, I hope you found this one to be enjoyable. I mean, there's not much to it, right? Like it's just pretty much as you take the differential of G1, G2, and G3, only one thing survives because you always have a repeated wedge. Like the first one, y wedge y or z wedge z is 0, so you're only left with the x, y, z wedges. And same thing happens for the other two, and you're just left with the divergence. This one, problem 3, everyone should have got this. I worked it in class, like verbatim, right? Like we did that in class. I literally did that in class. Problem 4, well here I'm kind of extending the discussion a bit, but like my point is simply that if we look at the work form corresponding to the vector field G, if that's closed, then that means that it could be that it's exact. In other words, it could be the differential of some function. In this case, it is the differential of x squared plus y squared plus z squared. So yeah, this is in fact the normal field to, oh, come on! I meant to put equal to a constant over here. So this is a mistake. Like if you told me the solution is, if I have an exact equation, right guys, and you tell me the solution is f of x, y, z equals x squared plus y squared plus z squared, I will take off points. Because that is not the solution. The solution is f of x, y, z equal to a constant. The solution set to that is the solution to the differential equation. F itself is just a step in that journey. All right, it's not the solution. Is it almost the solution? Yes, it's very close. I don't take a lot off, but I do want you to understand the distinction between these terms. And this one, on the other hand, after you calculate like d omega h, it's non-zero. Therefore, this can't be the normal field to some surface, because this is not h is not the gradient of some function. Is all I'm saying. On the other hand, c is the gradient of some function. It's the gradient of sine of xy plus 1/2 sinh of z squared. That equal to a constant. Oh, look, I got the constant down here. Yay. Any constant, this gives you I don't even begin to know how to visualize it, but I can tell you that that's the normal vector field to it. Yay. So anyway. Obviously, I didn't talk about that in class, but it's kind of a natural extension of what we were talking about. Yep.
Should we expect our test to look more like these homework problems or more like your past tests?
Is there a difference?
I assumed so.
Huh. Well, let's take a look. So here's an integral vector field problem. So that looks an awful lot like one of the ones I gave you, actually. Find the explicit this is a linear problem. Actually, this looks an awful lot like one of the ones I gave you. This is apparently an exact equation. I mean, this could happen. It's integration by parts, I think. You guys can do that. Here's a substitution problem. This is literally one of the problems we talked about today. Orthogonal trajectories. I might have worked this one today as well. Seems to be a creature of habit here. Oh, this is part of a different structure of the course. All right, so I was doing things differently. You can ignore all this, obviously, right? All right.
No lagging vectors.
Not yet, no. All in good time. Here's a slightly older one. I do allow you a 3x5 inch card, front and back, just two sides though. So, you know, exact equation, yeah, that's integral curves, explicit solution, all right? This is definitely a possible problem. You know, given a force, find the velocity as a function of position or a function of time. We have done examples like that in class. That's the larger point. If I've done an example in class, it's fair game. State the general real solution of this thing. We've definitely worked these. I've found this to be a pretty nice problem format solution. Like if I want to test if you know how to set up the particular solution, I can give you a multiple choice question and see if you understand how to do it. It's a very easy way for me to grade. This is what I want to talk about before we go today, guys. This one doesn't do it though. Rats. Oh man. If you look at my tests, I guess this one doesn't do it, but a lot of times I use superposition. That's something I haven't emphasized nearly enough in here, but what does superposition say? It says that if you have L of y1 equals to, say, f1, and if you have L of y2 equals to f2, and if L is a linear operator, then L of c1 y1 plus c2 y2 is equal to what? C1 f1 plus c2 f2, right? So what does this mean? Why am I talking about this? Well, I like to give a problem on the test where I give you the same L in two different parts, all right? But then the third part is just for free. So like maybe the first two problems, you're solving it for one f1, solving it for a different f2. So like, for example, you might have like y prime prime plus y equals to, you know, t cubed, and y prime prime plus y equals to sine of t, right? And then maybe the third problem is y prime prime plus y equals to 3t cubed minus 7 sine t, right? So if this has yp1 and this has yp2 as its solutions, you can just use yp equal to 3yp1 minus 7yp2 to solve that guy. So that's an idea I have not talked nearly enough about in here, but I'm talking to you about it now. So this is superposition. If I have the same differential equation but different forces, if I find out how the system reacts to one force and how it reacts to another force, then I can extrapolate from that by linearity how it reacts to a sum of such forces. And it, you know, just like this. But anyway, I'll see you guys Wednesday, I suppose.